This video is the first of a series of videos that I plan to make on how to build an 8-inch Jones-Herschelian, more commonly known as the Chief or Chief Spiegler. That's a name I gave it in 2008 when the article was published in the November Sky and Telescope. This wasn't the first catadioptric Herschelian or lens-corrected Herschelian. Bookroeder and Maxitov had previous designs, but this one differs because it requires a parabolic primary, much the same as a Newtonian. And in fact, some Newtonians can be converted into a Chief. It should look pretty much like this 6-inch Chief shown in the picture here. The Chief is an unobstructed design, and it uses two lenses, a plano-convex and a plano-concave lens, tilted to correct the aberrations caused by tilting the primary. The secondary I'm using is round, but there's many different ways you could fold this design, but I'm choosing to fold it back so that the eyepiece is in a convenient location. Here's a close-up of the two correcting lenses. You can see that they're tilted towards each other. They are Newport lenses, KPX 211 and KPC 064. Mounting of these two lenses is the most critical part of the Chief design. The Chief has exactly the same amount of coma as a Newtonian, and at f12 there's hardly any there, so over a half a degree field it's diffraction limited. And here are the spot diagrams of the 8-inch f12. The commercial lenses that I'm using are plus and minus 500 millimeters focal length, and they have the same radius. In order to tilt the lenses, they have to be separated, of course, but this separation causes a small amount of axial chromatic aberration. Small amount shown in the picture here. At f12, this isn't much of a problem, but for faster Chiefs, the problem becomes more serious, and then you need to have to use lenses with different radiuses. Here's the optical prescription for the 8-inch Chief. You see the primary has a radius of 192 inches, and the lenses are 10.173 inches, concave and convex. Under thicknesses, the primary is separated from the secondary by about 70.5 inches. Then the secondary to the first lens is 14 inches. The two lenses are separated from each other by half an inch. And then the back focal length is roughly 11.5 inches. In the tilt column, the primary is tilted 2.5 degrees. The secondary is tilted 15 degrees. And the first lens is tilted forward 11.84 degrees, while the second lens is tilted backwards by 7.76 degrees. And the final image tilt is about 1 degree tilt. The last two columns are the ZY global coordinates of all the components in the system and the image plane for the last one. You can use these numbers to do an optical layout in CAD. What I like about this Chief design is that it's unobstructed. It still has the good color correction and a reflector, but it's very lightweight and the eyepiece position is very accessible. And it fits very well on a altazimuth mount, like my 6-inch shown here. Compare this design to an 8-inch apomatic refractor on a massive German equatorial mount. I think you'll see that it has a lot going for it. The 8-inch f12 primary is not commercially available. I did this one myself, but it's an easy project for the first-time mirror maker to try. If not, then there's plenty of mirror makers that would be willing to make one for you. It could even be left spherical because a sphere is only going to have a 10th wave deviation from a parabola. The primary for a Chief needs to be really high quality, but on these long f ratios that's easy to do. The secondary is nearly circular, so you need to find a 3-inch diameter optical flat. And I'd recommend using a optical window from Surplus Shed, part number L10768. You can check both sides on an optical flat and pick the best one. The secondary could have a number of rings of power, but it does need to be free of irregularity, which would show up as the fringes not being perfect circles, or straight lines if it does happen to be truly flat. And here's one flat I got from Surplus Shed a while back, Pyrex. And this is for the secondary. And it's got one fringe of power, but no irregularity. Rings of power on the secondary are of no consequence. And here's another optical window I got from a Surplus Shed. This is the better side. Sometimes you need to take a piece of paper and tissue paper and then pull it up from underneath it to get rid of dust. That helps you see the fringes. And this part's also pretty good. It's not a 10th wave like they say, but it's certainly good enough to use as a chief. I've got about a half a fringe of curvature. That's no problem at all. And here's the convex lens. It's pretty good. It's definitely a quarter wave. And this is the negative lens. It's it looks like it has about one ring of power and a little bit of regularity on the edge, but that's only going to affect the field position. That's a good lens. Now, since they're both the same radius, you can check one against the other, and it's the coating makes it real hard to see. If you see true circles, that's good. That's the way it should be, because it's a differences in the rings of power. That's one way you can just check both of them together. Now, finally, if you don't happen to have a optical flat, one test you can do, which was suggested by Dick Brokrutter, is to put 3 pieces of shim or pieces of tape between the curves, and put the 2 curves together, and then put tape around it, and it becomes an optical window. And then you just simply mount this in front of a refractor, if you have a small refractor, and do a star test on it. You might want to only check about 80% of the aperture in case there's any rolled edge or something like that. But this is another way you can test the 2 lenses together. Now that I've got all the optics, I can start the construction of the telescope.